Okay, so yeah, good morning. And yeah, so I'm gonna talk mostly about multiferroicity and magnetoelectricity in two-dimensional system. Yeah, very quick introduction here, mostly to thank, I lead a small group at the moment in Chieti, and I would like to thank Paolo Barone and Danila Moroso, who are the main author of what I will show in the talk. I will, move soon from Chieti to the University of Milan in about a week. Okay, so I'm a density functional theorist, and I work on, recently I moved a lot to the magnetic system. Okay, there's no need to introduce the class of materials. Yeah, with this, you can, play Lego and also bend and slide. So they are, interesting material from many aspects. So the materials I will focus on are basically nickel halide. So these have a octahedral coordination. There's a small trigonal splitting out of plane. They are edge-shared octahedra, and the transition metal atoms are arranged in a triangular lattice. So first of all, I will focus on nickel halide. This is the 8. Which means that I fully fill the T2G shell and half fill the EG shell with 2 Bohr magneton on each nickel side. And these material were already studied back in the 80s at the bulk level. And already at that time, some complex magnetism was found to emerge. So the question now is what happens at the monolayer levels. The first question we tried to answer was whether they can, 2D magnets can show very complex helical, complex pigmentation, non-collinear or even non-coplanar. Okay. Frustration, just one slide. Okay, so because this is very important for what I will show you later. So if I have a triangle and I have an antiferromagnetic coupling, then I have exchange frustration, right? So the system doesn't know well what to do. If it aligns collinear up or down, then it frustrates one of the branch of the triangle. And so the system will end up in a kind of a non-collinear system as a compromise to optimize the energy of the different exchange interaction at play. And this is particularly relevant in several crystal systems, in 2D on triangular lattice on Kagome, and in 3D typically in pyrochlores. Even if I have a single chain, I can have exchange frustration. So if I have, for example, a second nearest neighbor, which is very large and antiferromagnetic, then if there is a strong single ion anisotropy, this will end up in a single chain of Ising spin, up, up, down, down, because in this way the system can at least optimize the J2, which is always antiferromagnetic. If the anisotropy is not that large, then the system will probably adopt like a spiral state. So it will evolve from one direction to continuously to the other. Helical or cycloid, but it's anyway going to be a spiral. So from DFT, one can extract the exchange coupling parameter by mapping on a, for the moment, Heisenberg Hamiltonian without spin-orbit coupling. And this is what we get for nickel, in this case, nickel I2. So we get a very strong ferromagnetic J1, first nearest neighbor. Then J2 is, basically negligible. And then we also get a strong antiferromagnetic J3. So if we remember now the chain model, if we try to place this interaction on the lattice, then first nearest neighbor would like to be ferromagnetically coupled. We place all them up. But then when we try to satisfy this J3, this will give rise to frustration in the triangular lattice. If I place it up, then the second nearest neighbor is happy, but then the first nearest neighbor is not happy. So we expect, given this exchange constant, we expect some non-collinearity in the system due to the large exchange frustration given by the ratio of J3 to J1. Okay, this is without spin-orbit coupling, but we know that in principle Heisenberg Hamiltonian is not a complete description of the system. We'd better describe the pair interaction with the matrix, and one can always decompose a matrix in an anisotropic term, in an antisymmetric term, in an asymmetric term, which from the microscopic or the nomenclature adopted in the magnetic community, this corresponds to the Heisenberg term, the isotropic one. The antisymmetric is generally labeled Cauchy-Moria interaction. And then there is this part, which is the anisotropic, so-called anisotropic symmetric exchange, which is usually pretty much neglected by the community, but it actually turns out to be relevant in this system. Okay, Heisenberg wants to couple with a certain sense, parallel or anti-parallel, the two spins, but they are isotropic, right? So whatever direction in space the spin will have, it will give the same Heisenberg term. Cauchy-Moria is going to count the system in a preferred direction. It's a chiral interaction. And an isotropic exchange is also a source of anisotropy. It's called a two-side anisotropy, right? It tends to align in a certain direction the spins. So it's like single ion anisotropy, but the effect is like the single ion anisotropy, but it comes from a pairwise interaction. And DM and anisotropic exchange, they are originated in the spin-orbit coupling. Moria knew it from the. And so in our case, we have inversion symmetry in the bond and in the system, so there's no Cauchy-Moria in our nickel halide. And because of the symmetry properties of the crystal, this is the form. So we are allowed to have three different diagonal terms and only one off diagonal term, which is gives rise to a symmetric. By the way, let me advertise. We are now building a database called Amaranta. So we are trying to automatize the script, basically, the calculation of exchange coupling constant in a tensorial way for all the 2D magnets. And this is done, maybe some of you have seen already the poster by Federico Orlando yesterday. And this is also done by the group of Cesare and Marco Gibertini and Antimo Marrazzo. If you're interested to know more about this availability of exchange coupling parameter calculated by DFT, okay, so what do we get in the nickel halide? So for nickel chloride, even if we allow spin orbit and even if we allow the tensor origin of the exchange coupling constant, we basically get a Heisenberg description, right? There is only one parameter, no off-diagonal term. If we now move to nickel bromide spin orbit coupling, it increases a bit. Then we start having three different off-diagonal terms, and one off-diagonal term pops up. And the effect is much larger if we now move to nickel iodide. So we have three very different JXX, YY, and ZZ, in a very strong off-diagonal term. Okay, and this, okay, because transition metal is constant across the series, the spin-orbit coupling that gives rise to this effect must be the one of the ligand. So it's the iodine that basically leads to this, to the emergence of this strong anisotropic exchange. So the ratio between off-diagonal and diagonal is like, I don't know, 20%, so it's pretty large in nickel iodide. Okay, then if we try now to see what is the ground state of the nickel halide, we need to move to like a Monte Carlo or a multi-scale approach. And so we typically did Monte Carlo simulation, and this will allow us to see what's the ground state and move to finite temperature, or also much larger system compared to what we can do. Just a word of to explain the notation. So we have three-dimensional spin here, but I will show them by projecting them on a plane and showing the arrows. So the arrows show the projection on the plane, and the color scale will tell us the direction out of plane. And so for nickel bromide, what do we get? So here you should recognize basically a helix. So you see that there is a propagation direction, and then my spin will circulate and propagate from side to side perpendicular to the propagation direction. It's typically like a proper screw helix. And if we now calculate the specific heat, this will give us a pretty low temperature, which we expect, right? Because it's a strongly frustrated system. They usually have very low ordering temperature. This depends on the U, blah, blah, blah. But then it's going to be of the order of like 20 Kelvin. So there's nothing that we didn't expect, right? Because we know there's a frustration, and we know one can have a spin helix. What we didn't expect, what we got for nickel I2. So for nickel I2, we got a much more complex picture. So we recognize some, the presence of some objects there. We went back studying the magnetic skyrmions, which there's no need for to introduce in this audience. Just let me say that to calculate the topological charge of this skyrmion, or anti-skyrmion better, what we calculated was actually taking each of the triangle in the lattice and then calculate the scalar spin chirality. So we cross product two of the spin and then make the scalar product with the third one. So this is, of course, 0 if we have coplanar spin, but as soon as we start having non-coplanarity, then we might have the emergence of a topological charge. So we took these as our order parameter. And so we basically, by calculating this topological charge, we actually discover that there is an anti-skyrmion lattice with a higher order character. So Q is equal to 2. So it's an anti-skyrmion of higher order. And when we discovered back in 2020, this was the first example of skyrmion in a 2D magnet system. And it's not driven by cellulose chemoria as it often happens, right? Because the M is 0 by sigma. So it must be driven by something else, which is probably the coexistence between a strong anisotropic exchange and also exchange frustration in the system. The underlying system is already a bit unsure about what to do. Okay, I must say that the anti-skyrmion is very exciting, but actually looking at the energies, there's basically like an isoenergetic arrangement between the anti-skyrmion and the helix. So actually, even in nickel I2, one can basically get the helix as the ground state. And actually, for what I will tell you in the rest of the talk, it seems that in nickel I2, you more have a helix than the anti-skyrmion. But from the DFT point of view, we can't really say which is. Okay, so the question to the answer to can we have a very exotic spin texture in a 2D system? The answer is yes. Even a helix is complex enough, and anti-skyrmion would be even more complex, but definitely one can have non-collinear arrangement in 2D magnets. Then the following question is whether this complex spin texture can give rise to ferroelectricity. And so let me go back to very quickly how if ferroelectricity can emerge from a complex spin texture. And this, we really need to jump back in the beginning of 2000. So it was shown that a spin spiral can give actually purely by electronic means to a polarization. And if you switch the sense, the chirality of the spiral, polarization will switch. This was very clearly shown in the manganese, where it was shown that the emergence of polarization actually happens at the Néel ordering temperature. So there's clearly a strong coupling between ferroelectricity and magnetism. Okay, and okay, these, I mean, they're very improper ferroelectric, right? Improper in the sense that the primary order parameter is an electronic order parameter, which breaks inversion symmetry, and as a result, it gives rise to polarization. And so these electronic degrees of freedom can actually be spin, or orbital, or charge. So any kind of electronic order that gives rise to breaking of inversion symmetry in a polar way can in principle give rise to ferroelectricity. This was very clearly, established for oxide, but it was not established, and there was no example in the literature when we start this collaboration with Riccardo Comin at MIT in 2022. And so the question we asked was whether, this phenomenology that was well known for 3D material, specifically oxide, could actually happen at the monolayer level. So if we have a monolayer level, can we have like spin-induced ferroelectricity? And so Riccardo, grew crystal and then exfoliated monolayer and bilayer and few layers. And then they did nonlinear optical characterization by second harmonic generation and optical birefringence. And then by doing this characterization, they could actually observe a signal which actually, whose temperature decreases if I move from 4 monolayer to 3 to 2 to 1, but even at the monolayer there is some signal, right, which tells us that there must be some kind of ordering happening even in the monolayer. They also did a symmetry analysis from this second harmonic generation, and that was very helpful for us because from this they could tell us actually that there is a twofold symmetry in the system, which means that we cannot have an anti-skyrmion because this would have a threefold symmetry. So this is why we think that the magnetic ordering is probably a helix, consistently with the twofold symmetry. So starting from this, we consider a spin helix, and then we asked whether this could give rise to ferroelectricity. So to explain the spin-induced ferroelectricity, one usually invokes a model based on spin current, which was originally proposed by Katsura and Boy. And basically, you can link the polarization to the cross product of two spin, cross product with the vector connecting the two spin or propagation direction. So for a spin helix, this would give 0, right? So we don't expect, based on this simple model, any polarization. But in principle, you can generalize this formula by allowing in front of the S1 cross S2 a matrix. And by DFT, you can actually calculate all the components of this magnetoelectric coupling tensor. And so if you have, okay, then this is what? This will give you the polarization that you have by simply counting to spin. So however you count to spin, you can have some polarization. But then, of course, you have to sum over all the couples that are present in the system to see if maybe the polarization cancel and you don't get any macroscopic polarization. Of course, the KNB picture is a special case of this matrix, right? You only have one element in the matrix, and it's an antisymmetric matrix. And so basically by DFT you can calculate all the elements in the tensor. This was proposed by Zhang in 2011. It's not our work. We just estimated the magnetoelectric coupling tensor. And so you see that the DFT tells you that it's absolutely non-K and B. There are many elements that deviate from the simple K and B picture. And if you actually sum overall the lattices by proper rotation, then you see that you get a polarization which is in the plane and it's perpendicular to the propagation direction of the spiral with ordering temperature of like 20, 30 Kelvin for the monolayer, which is about quite good agreement with what Ricardo saw. So you have ferroelectricity here induced by the spin. And this is in very good agreement then with the experimental finding by Ricardo. Okay, so we now know that the spin texture can give rise to ferroelectricity. So one can have a two-dimensional multiferroics. The question is, can we design more? Can we find some other system in which these effects are also present? And also, from people who are, have been in this community for long, many of the 3D multiferroics are oxide, right? So the effect of the anion on ferroelectricity was never really proper investigated because you always have oxygen, right? But here you have many halides, so you can investigate the effect of the anion on ferroelectricity. And so to address this question, we took a look at the cousins of the nickelates. We took a look at vanadates, and we consider vanadium chloride, bromide, and iodide. Here we only have 3 spins, and so we have a 3-Bohr magneton with this 3 half. And so here the exchange coupling constant tell you that there's a strong antiferromagnetic J1. So J3 is not strong, so that the physics is different compared to the nickelates. So you have a pure, typically you have a pure 120-degree spin arrangement. The first exchange coupling is antiferro, and you have the situation that I just showed in the beginning of the talk. What we actually couldn't say is whether the spins are in plane or out of plane. The anisotropy is really, kind of small, and so we consider both spin arrangement with spin in plane and spin out of plane. And so again, one can estimate polarization from, here you can also do the Berry phase approach because the spin texture is not too complex. It can be also simulated by DFT. And so the first observation that you do, this is spin orbit driven, right? And this I forgot to say, but also the polarization that you have by writing like MS1 cross S2 is killed if you kill spin orbit coupling. So this is a spin orbit driven phenomenon. However, so if you kill it, it's 0, but spin orbit coupling is not the only factor playing a role. Otherwise, it would increase in vanadium. Vanadium iodide would be larger than in vanadium chloride. So spin orbit coupling increases in atomic spin orbit coupling increases if you move from chloride to iodide, but the polarization doesn't really follow the same trend. And I will come back to this point a bit later. Also here, if you change the direction of the spin configuration, so if you move from a spiral in plane to a spiral out of plane, the size of polarization changes, so it's relatively strong. Okay, these are small values of polarization. These units are 10 to the -5 electron per angstrom. So it's really small. It's order of magnitude smaller than what you have in barium titanate, but this shouldn't surprise you, right? This spin-induced ferroelectricity is always much small. It's a small effect. However, you can modulate if you change the plane in which the spin. Okay. One needs to show, if to sell it as a ferroelectric, it needs to switch, right? So the mechanism of switching here needs to involve some changes in the spin configuration. And so to reproduce a so-called double Welling ferroelectrics, we basically model it by progressively rotating the spin from, let's say, 120 degree to the ferromagnetic state to the 120 degree with the opposite chirality. Right? And so this corresponds to theta equals 0 for one chirality, theta equal 90 for the ferromagnetic configuration, and theta again back to 0 if it goes to the minus p state, and you see that there's a double well, so really a ferroelectric. The other thing we try to do, although with a bit of technical issues, we try to apply an electric field. Okay, so this polarization here is out of plane. We try to apply an electric field out of plane. This should stabilize one chirality over the other. So if you don't have any electric field, P and minus P are degenerate, right? But as you start having an electric field, you should be able to stabilize one clockwise over counterclockwise. So we plotted the energy difference between the two chiralities as a function of the electric field. This is 0 without electric field, and then it increases linearly, at least for this electric field, as we increase the electric field. So one should be able to stabilize one chirality over the other by applying an electric field. Yeah, so I told you that you don't, spin-orbit coupling is not the only effect that plays a role. So what else can play a role? So we thought that structural effects could, be worthwhile to be investigated. And so we did simple tests, like one of these computer experiments that we like so much. So let's say we have 3 different lattice constants, right, for chloride, bromide, and iodide. And then we did a simple chemical substitution. So for example, we took the lattice constant of vanadium chloride, but we replaced bromide and iodide, and similar for the lattice constant of vanadium iodide, we substituted by chlorine and bromide. And the effect on the polarization on the dipole is pretty large, is actually very large. So you can see here the 3 different lattice constants and 3 different chemical identities of the compounds. And so probably the origin of this non-linearity as a function of spin orbit is actually coming from the coupling or hopping that you have in the electronic structure when the atoms are simply closer or at simpler, simply connected by different, nickel, vanadium chloride, vanadium angles. So the structural effects are really important. So it's a spin orbit driven effect, but the structure is very important. Okay, so can we design more 2D multiferroic? Yes, vanadium halide are an interesting class of system that one might look at. How much time I have? Do I have like a couple minutes more? Okay. Yeah. Then maybe very quickly, I will. So far I showed you spontaneous effect. So they order magnetically in this way, and then they give rise to ferroelectricity, both the vanadate and the nickel. But we might also, induce some ferroelectric polarization by applying a field. And so to study this, we took a class of 2-dimensional magnet, so like manganese, phosphorus, then a chalcogenides, selenium or sulfur. And so in this is an hexagonal lattice. It's certainly anti-ferromagnetic, but we couldn't say very well, again, because with our method we cannot really predict the anisotropy, is whether they are in plane or out of plane. So we consider both of them. And so then we tried, okay, so assume we have the spin in plane. We try to count them, mimicking the effect of a magnetic field. And so if we count them, then we have a polarization emerging, let's say, out of the board. If we apply a magnetic field, let's say perpendicular to the board, then the spin would count out of the plane, and this will give polarization in the plane. There might be a third case in which the spin start by in this, if the spins are out of plane, then if we apply a magnetic field in the plane, and so the spin will probably, if they are like this, they will cant, there will be a small canting in the direction field, and this will give us polarization in the, again, in the plane but perpendicular to the magnetic field. So this is just a sketch, but of course we did calculation. And we could quantify to the extent of a DFT plus U approach, but certainly the mechanism is there. You get a polarization and you also can switch it, right? So if you switch the direction of a magnetic field, then polarization will also switch. So this tells us also that you can have a magnetically, if you apply a magnetic field, then you can induce ferroelectricity. So it's a kind of magnetoelectric. This concludes my talk. I think I showed you that with this, Lego field in which you can, stack everything on top of everything. Now you can have a multiferroic brick that you can play with. This I would like to close my talk and thank for your attention.